In this video, we'll be looking at another implementation of the depth-first search traversal. In the previous video of the graph series, we have seen the backtracking implementation using recursion. There is an alternative implementation of the depth-first search algorithm that does not involve recursion. An iterative approach to the FS can be done via a stack. The stack is used to store the discovered node, not the visited one. The visited nodes can be recorded via a set or an array. In fact, the stack emulates the call stack of a recursive function. The first step of the algorithm is to choose a starting node. Again, it does not matter which one you are choosing. In our case, we start at vertex 0 and we push it to the stack. Next, we pop the vertex at the top of the stack, currently vertex 0. From vertex 0, we explore all the outgoing edges that have not yet been used. The first edge is, for example, edge 02. The node 2 is unvisited, and we push it to the stack. There is another unvisited outgoing edge from 0, so we are not done yet with vertex 0. We must explore edge 01. Vertex 1 is not visited, so we push it to the stack. There are no more edges to explore from vertex 0, so it is labeled as processed. Now we can pop the element at the top of the stack and reprocess it. Vertex 1 is the node we need to explore next. First we look at edges from 1 to 2. Vertex 2 has already been visited, so we move to the next edge, in this case the edge from 1 to 3. Vertex 3 is unvisited, so we push it to the top of the stack. We are done with vertex 1, and it is labeled as processed. Next, we pop the vertex at the top of the stack, that is, vertex 3. We keep adding the unvisited node we discover at the top of the stack, and pop the element from the top of the stack when a node has been fully processed. We do so until the stack is empty. The stack is empty. However, we still have to explore the remaining outgoing edges from 2 that have not yet been explored. We are not finished yet. From vertex 2, there is only one edge left to explore, the edge from 2 to 5. Vertex 5 is unvisited, so we push it to the stack. We are done with vertex 2, and we pop the element at the top of the stack. Vertex 5 has no unvisited outgoing edge, so it is a dead end. The stack is now empty, and we don't have any vertices being processed. We have finished our depth-first search traversal. The next step is to write the pseudocode for the iterative implementation of the depth-first search traversal. The procedure takes two inputs, the graph to be traversed and source, the starting vertex for the exploration of the graph. Before starting the exploration, we need to set up some containers, a stack to store the vertices being visited, and an array labeling vertices as visited or not. First, let's set up the stack being visited to an empty stack and then push to the top of the stack the starting vertex source. Secondly, let's set up an array of size v, the number of vertices in the graph, and initialize it to false. False means the vertex has not been visited. As we have added source to the stack, we can label the vertex source as visited. Now that the setup is done, we can move on to the main body of the algorithm. While the stack is not empty, we need to do the following. Take the vertex at the top of the stack and process it. For example, just printing its value. Once processed, we look at all its neighbors one by one. If a neighbor has already been visited, that is, it is in the stack or we have processed all its neighbors, then ignore it. Otherwise, add the neighbor to the stack and label it as visited. The time complexity of this algorithm is the same as the one using recursion. That is, big O of V plus E, where V is the number of vertices and E is the number of edges. Again, using an adjacency list representation on a sparse graph would result in a better performance than using an adjacency matrix. DFS has many applications for solving problems for both directed and undirected graphs. We will be exploring some of them at a later stage. There is another alternative to depth-first search traversal of a graph, the breadth-first search algorithm. This approach also has many applications for solving other types of graph problems, and it will be the subject of another video.